Okay, now we're going to solve some applications for first order derivatives. And if you look here, these right here are like real physical examples. You know, physics uses a lot of calculus, and so no wonder we're looking at those kind of examples here. So looking at the first one, number 9, it says a charged particle of mass m and charge q moving in an electric field E has an acceleration a given by a equals qe divided by m, where q and e are constants. That means our variable is m, so that's why they want us to find dA dm. What they're asking us to find here is what is a prime in terms of m. Well, that's not too difficult. Okay, we're going to write this out here. We're going to say a equals qe divided by m. Our variable is m, so what we're going to do is we're going to write it in terms of an exponent so that we don't use any kind of quotient rule. Q e m to the minus 1. I can bring it up, negative exponent rule. Now to find my quote unquote a prime, which they actually use Leibniz notation, they say dA divided by dm. Okay, I'm just going to use the power rule. So the negative 1 is going to come down and I'm going to subtract 1 from it. Okay, so that's not too bad. Negative QE m to the minus 2. Okay, because we have to bring the power down, the negative 1, and then subtract 1 from it. So if you want to express this using only positive exponents, you will say, well, it's negative QE divided by m squared. This is what dA dm looks like, or a prime in this case. So there's your answer there. Really nice little application. And of course you'd have values to plug in and all this stuff, and you'd be able to find the rate of change of the acceleration in this system. Okay, so let's take a look at another example. All right, another one, if you will, if you caught the reference to some famous DJ guy. Anyways, a heat engine is a device that converts thermal energy into other forms. The thermal efficiency E of a heat engine is defined by E equals Q sub H minus Q sub C divided by Q sub H, where Q sub H is the heat absorbed in one cycle and Q sub C is the heat released into a reservoir in one cycle. And Q sub C is actually constant, so that's not the variable. The variable here is the Q sub H, because notice what they want us to find is the rate of change of the thermal efficiency, which is dE dQH, dE divided by dQH. So what we're going to do to find this quote unquote E prime, because that's what they're asking here, what is E prime, the rate of change of the thermal efficiency, all right, is we're going to apply here the quotient rule. We have to. We've got two functions with the variable on one on the top, one on the bottom. All right. I suppose we could bring it up and we could do some algebra, but let's just apply the quotient rule. I think it's just so much easier in this case. So if I've got my high, which is Q sub H minus Q sub C, and I've got my low, which is Q sub H, well then I'm just going to take the derivative. Now, what we're going to do is we're going to pretend that they're variables like x. So suppose this was x minus some constant, the derivative of x then is just 1. So the derivative of Q sub H is just 1 there. This Q sub C is going to be 0 because it's a constant. They told us it was constant back over there. All right, so d low again then is just going to be 1 because it's just the derivative of that single variable. So pretend it was like x again, and the derivative of x is just 1. So what we're going to do is we're going to multiply now low d high, so that's going to give me Q sub H times 1, so Q sub H the low d high minus high d low, which is q sub h minus q sub c times 1, which we really don't need to multiply by. So I'm just going to put minus q sub h minus q sub c, looks something like that, all divided by low, which is q sub h square, looks something like this. We're going to distribute like that. I'm going to get q sub h minus q sub h plus q sub c divided by q sub h square. All right, my q sub h's cancel. All right, and then I'm left with, if I'm looking for my derivative, e prime, because that's what this is, e prime is going to be q sub c divided by q sub h squared. So that right there is my derivative using the quotient rule here. All right, but otherwise this would be how we would calculate the rate of change of the thermal efficiency of this system in this heat engine process. Okay, so not much to it. You just have to read very carefully to find out what's constant, what's the variable. But if you can do that, I think you'll be okay. So I hope this video was helpful. And as always, like and subscribe.